Dobra, zaraz to zrobię.
Okay, I think we can start. So it's 4 p.m. Our today guest is Michał Siwak. Michał is working at the University of National Committee of Education in Kraków. And he's also involved in many observational projects on Suchora Observatory in Poland. He did his PhD in Jagiellonian University in Krakow, then he spent some time in Toronto, then he was back in Poland, then in Hungary, and he's back in Krakow. And he's gonna tell us about the young stellar objects, young stars, and all the details will be in the talk. So thank you.
Well, thank you very much for the invitation. So I will be talking about different aspects of accretion in young stars, mostly from the observer perspective. I will show some examples of ordinary T Tauri-type star accretion, which young stars encounter during class 1 and class 2 evolution stage. I will also show some examples of FU Ori-type enhanced accretion. This is the evolutionary scheme. The pictures are showing how the stars is evolving from the collapse of the molecular cloud to formation of disk around still the young star. I mean now about class 1 stage. I'm showing both halves of the slide show the same, but actually the left one shows better pictures, but the right one shows spectral energy distribution in lambda, which I prefer. So we see that as the evolution progresses, we see the star first from in millimeters and radio wavelengths, then in far infrared and infrared wavelengths during class 1 stage. During class 2 evolution stage, we see both the disk and star, and there are some relative distribution between stellar and disk light is shown here also. And in the class 3 stage, the disk is almost absent, and we mostly observe stellar light. This is the disk. The other name of the disk during class 3 is like debris disk, something like that. The evolution during the light curve, the variability of class 3 stars, in other words called weak-lined T Tauri-type stars, is usually caused only by rotation of stellar surface, spotted stellar surface, with non-uniformly distributed cold spots. In some cases, here I'm showing examples of 4 stars observed by MOST, almost 15 years ago, MOST satellite. Sometimes we see evolution of the shape from one to the next period, which is probably caused by differential rotation. And the best summary probably was given in this decade by Agnes Kospal, my colleague from Observatory, during Protostars and Planets 7 conference in Kyoto. If you are interested in this topic, please go to follow this link and watch the great review talk. But I will just concentrate on, in the next few slides, concentrate on the aspects which I'm studying currently, or I studied like 5-10 years ago, but I didn't talk so far here, at least. So I was showing the class 3 variability on that slide, but moving back towards younger ages, we can also observe class 2 stars, classical T Tauri-type stars. In the past, it was difficult to characterize because of the daily breaks in the observations. After most satellite launch in 2008, Professor Sławek Ruciński started new era in the time variability studies of classical T Tauri-type stars using by analysis of long uninterrupted time series gathered for TW Hydra. I joined this project in 2009 in Toronto. We, together with Sławek and the MOS team, we investigated other interesting classical T Tauri-type stars. I was actually talking about the stars 11 years ago when I was here. I will not repeat the same, but I will just show something obtained very recently. Yes, very recently for T Tauri using Kepler and TESS, because most is decommissioned. Of course, on the world, in the meantime, in the last decade, a few groups were created on the world which completely dominated this field. I even joined one group, Penelope, which is led by Carlo Marnara from EXO, which is using combined TESS, HST, and VLT data. I will not talk about those results because I didn't prepare a single first author paper during collaboration with this group. I will just concentrate on results obtained for T Tauri itself, which got the name of the entire group T Tauri-type stars. So luckily in 2015, I got 16 cadence Kepler observations of the star. At the time, it was necessary to submit proposal to get 60-second cadence Kepler observations. And we see the light curve on the upper plot. Krzysiek Kamiński from Poznań, using Roman Baranowski telescope, provided high-resolution spectroscopy. And the moments when the high-resolution spectroscopy was obtained is indicated on the light curve by the red circles. And what we see on the light curve is that the variations are fairly regular. So we see fairly almost the same, something which is almost regular, not strictly periodic, but something which can allow us to determine, for example, the rotational period of the star. That one plot shows broadening functions of the star calculated from the spectra obtained in different phases. When I calculate the phase, using this reference time, and I determine period from frequency analysis, I phase forwarded the broadening functions, which show that here we see the entire rotational profile of the star, but here is some brighter strip, which is changing the velocity from negative radial velocities to positive, and it happens at phase 0.5. This is Kepler light curve phase forwarded with the period 2.81 days, which I found. So we see that the variability of the light curve is caused by most probably hot spot on the star. It is a artist picture, not necessarily for T Tauri, but for many classical T Tauri-type stars. And T Tauri is actually observed almost from the pole. So we see some modulation when the star rotates. And actually, I didn't publish quickly those results. In the meantime, it turned out that TESS will be observing constellations along the ecliptic region. And in 2021 and 2023, it turned out that the light curves are more chaotic than during Kepler observations. Okay. The next two plots show long-term variability of the Tauri. This plot shows AFSO light curve from 19th century to the present day. Here is the same obtained by AFSO ASAS and sometimes from Mont Suchora. And we see that after a long stage of nearly stable brightness, the Tauri started to show some major long-term dips, which is probably because the paper from this year is explaining this by obscuration of T Tauri-N, because actually I should tell this at the beginning. T Tauri is a triple system. What we observe in visual bands is T Tauri-N component, and T Tauri-S is infrared binary star, which is still hidden in the envelope, and we can observe T Tauri-S only in infrared light. Here I'm showing some analysis, wavelet analysis introduced by Sławek Ruciński 2 decades ago, which can be used to determine both the rotational period of T Tauri from Kepler observations. Here I'm showing the same Kepler light curve which was shown before, and test but the trend that the rotational period is not very well visible. The spectrum is dominated by many random signals which are not even quasi-periodic, and they probably reflect the conditions behind the rotation radius of the disk of the Taurian component. And using the spectra, both the Roman Baranowski telescope, high-resolution spectra, and low-resolution SAO spectrum, after correction on extinction, taking into account Gaia distance, we can determine mass accretion rate, and for that we use usually empirical relations established for some emission line by Alcala in the previous decade. And we got some results which I showed some examples, like that the mass accretion rate is of the order of 10⁻⁷ solar mass per year. It is fairly stable over the observing time. And it is similar to obtained 2 decades ago by some American observers. And here I'm showing examples of analysis of high resolution of emission lines, H beta, H alpha, and oxygen 1. Some variance I'm looking for the places or the regions which are showing the biggest variations. The blue is some normalized variance profile. The light blue is normalized variance profile. The dark blue is variance profile. And here's some correlation matrix which can which are used to find some positive or negative correlations among different velocity beams in the emission lines. I will not talk in detail because this analysis is still in progress. So I will probably present final conclusions in the paper, which will be hopefully submitted by summer this year. Okay. So T Tauri got the name of the entire class of classical T Tauri-type stars. It shows typical variability like many other classical T Tauri-type stars. Sometimes the light curve is more regular, sometimes it's irregular. So which means that the stars can switch between a stable and unstable accretion regime depending on the inner disk conditions. But from time to time, this quiescent stage is disturbed by some instabilities in the disk, either magneto-rotational instability or clamp impact to the disk or collision. I mean, in this sense, is that because sometimes stars are formed, usually stars are formed in pairs, and during close periastron passage, one component is disturbing the mass flow in the disk of the other star, and vice versa. And there is some instability in the disk, and it causes that at some point the mass is pushed toward the star at faster rate, and it needs to be accreted. And here we see some extra luminosity. Let's say this is typical luminosity during the quiescence. Here is the luminosity on that side. Here is the mass accretion rate. We see that the luminosity during FU Ori-type or during eruptive accretion rises by few orders of magnitude, here probably 2 orders, depending on the mechanism. And the same happens to the mass accretion rate. There are several mechanisms. I'm not going to discuss them in detail now. So actually, the old division was that eruptive accretion happens during class 2 stage, but now we see that it is more common for class 1 objects. It is the old division valid until 2010 was that young stars encountering eruptive accretions can be divided on FU Ori-type objects and EXors-type objects, which to show similarity with FU Orionis are called EXors. But the recent review talk given by Agnes Kospal, and which is included in the paper of Fisher et al. 2023, claims that in terms that the eruptive accretion, there are so many cases of different kinds of eruptive accretion that there is in fact not a strict division into EXors, FUors, but there is some smooth continuum, and depending on physical conditions in the inner disk and the particular mechanism, some stars show more characteristic features characteristic for FUors, some for EXors, and this is, yes, actually what we are studying in Budapest, what I was studying at Concord in Budapest. I concentrated myself on FU Ori-type stars because they last several decades or longer. The FUor stage has major consequences for the disk temperature and chemical evolution of the disk, protoplanetary disk, and also on the evolution of the star itself. And yes, 10 years ago, only 30 young eruptive stars were known, but now, thanks to Gaia and other surveys, we probably know about 100 or even more cases of young stars and going through the eruptive accretion phase. Yes, to characterize such stars, we usually use spectra obtained in infrared because infrared is the best region to quickly, which quickly can let us, to distinguish whether we have the case of FU Ori-type stars, of EXors-type stars. EXors or EXors-type stars show all emission all lines in emission, but FUors in absorption. And of course, the other major characteristic is the light curve. FUor outbursts are lasting for like many decades, sometimes 100 years. But EXors, sometimes few weeks, months, maybe a year, not much longer. And there are plenty of cases, dozens of cases which last for a few years. Those cases are intermediate cases, which show both characteristics of FUors and EXors. And yes, Gaia was vital in discovering, many new FUors. Here I'm showing examples of Gaia 17 BPI and 18 BVI, discovered and published in the previous decade. And I was analyzing, and recently I published results for Gaia 20 decay. Here I'm showing some light curves and the times when the spectroscopic observations were obtained. Some spectra, like low resolution spectrum obtained on Liverpool telescope Sprat spectrum, and high and low resolution spectrum obtained in infrared using NTT and IRTF on Mauna Kea. Some analysis of line profiles, some comparison. I will not discuss in detail everything, and some results of identification of major metallic lines using IRTF and not NTT spectra, and also SOFI, and also not CS as well. We usually prepare color magnitude diagrams using available optical and infrared data to check whether the brightening could be caused by reduction of extinction along the line of sight. Yes, this is not the case in this place because the vector is not always perpendicular, not always parallel to the brightening. And yes, we usually do some work to establish stellar parameters for the progenitor using color diagram. For prepared from infrared data, we can determine the extinction. Here the pluses are separated by +1 magnitude in AV. So by shifting this point obtained by 2 mass during pre-outburst stage to the line which is representing other than a classical T Tauri-type stars, we can estimate how much is the visual extinction on the light of sight to our progenitor. And usually we establish the class by construction of the spectral energy distribution using the pre-outburst data. And after deadening by the extinction, here are the same data which are shown here, but in the just flux, not energy. After deadening, we fit black body usually because this is sufficient. Of course, we can use stellar atmosphere models as well, but the accuracy will be not much better. And yes, some analysis of evolutionary tracks. Here I'm using the tracks computed by SIS a long time ago to establish the mass of the star. Yes. And usually after using post-outburst data, we prepare spectral energy distribution, and we are using our disk model written at Concoli to determine the disk luminosity and mass accretion rate. So we obtained typical disk luminosity, which is seen among FU Ori-type stars, and the mass accretion rate, which is only true for FU Ori-type stars. I was also another case analyzed at Concoli was Gaia 21 ELV. It was done. The work was done by Zofie Nagy. She probably presented those results here on separate talk some time ago. She also got that the star is typical FU Ori-type stars. And I also analyzed Gaia 21 VTI some time ago. This case is difficult to understand because, as we see, the Gaia light curve quickly went to the, maybe not completely, but to the quiescent phase outburst, which lasted maybe 3 months, and then the brightness dropped. But in infrared, we see that the brightness is still rising. And the same is in JHK bands, which I was observing the star last time on this Saturday, but the data are not reduced, but it is still bright in JHK bands as well. we don't understand what happens. Probably we're not talking data. This is low mass star, but probably we think that this is typical FU Ori-type stars, but the innermost disk light is more heavily absorbed than the older than the light coming out from the older disk regions. Here I'm going to show you the comparison of pre-outburst and outburst spectral energy distributions. Yes, this was find targets. We were using many deep surveys. Okay. Actually, now we still analyze. Our colleague group is still analyzing a few cases. Few are probably FU Ori-type stars. Around 10 more objects are probably new EXors or EXors-type objects or intermediate cases. Because Gaia mission is over, we are more frequently using ZTF survey. Also, there is another group from England which is using VVV survey, which is providing an enormous number of new eruptive star candidates. So recently, Lucas et al. Published and presented 17 new FUors. We are hoping that LSST will be delivering new alerts. And recently, our colleague group is collaborating with Michał Siwak from ISO, whose student prepared a list of over 300 FUor candidates. I did a short list using mostly Dehatom. I did the short list I was searching for stars to observe on IRTF at Mauna Kea, and this project is still ongoing. Yes, and we are, of course, using many other telescopes because the group is quite large, because there are people from Italy, France, which have access to different telescopes, and from Canarian Islands as well. Okay, this is typical situation how the remote observations from Mauna Kea look like. In my case, one computer to communicate with the telescope operator, and the second is VNC with the program to operate spectrograph and guider. It's quite nice work. Sometimes it takes 6 hours. It depends on the scheduling. Actually, it is quite convenient for us because the time shift is between Hawaii and us is 12 hours. Yes, I will switch to the last topic, which I'm going to discuss. Do we have a time still?
Yes, we have.
Okay. So I was discussing about large-scale effects caused by eruptive accretion on the previous slides. But some time ago, in 2010, led by intuition, I decided to observe FU Orionis with MOST. And here we see actually the picture from Wikipedia, which I found this week, when I was trying to show how the evolution of how the history of the light changes in FU Orionis. This is the quiescence, this is the year, and here is the present state, let's say present state. And actually my light curve obtained in 2010 is on the Wikipedia. I don't know who plotted this light curve, who put this light curve to the chapter. And yes, in 2010 we found that the light curve, but FU Orionis still, maybe the scale is not very well visible, but the light changes are not larger from here to here, from this peak to this bottom. Amplitude is like 0.1 magnitude. So we see some, let's say, this size scale to the big picture should be like maybe 0.2 magnitude in a magnitude scale. Yes. And in 2013-14, I organized longer campaign using most satellite and ground-based support from Montserrat and South Africa. And we discovered that the small, now here we see the most light curve, but the light curve obtained over almost 60 days can be divided by different segments, segment 1, segment 2, segment 3. Here we see some peaks and some intermediate peaks in between. Here we see some small scale oscillations, which we'll discuss in the end. And here we see something similar to the segment 1 and the same characteristic periodicity, but it's just like the different shape. I also obtained color. I prepared color magnitude diagrams, and I colored the points, based on the segment division, based on most data, based on that what we see in most data. I just put some regions from segment 1 and color it by segments. And yes, then we decided to explain cause variations in the different classes to construct this starlight synthesis model, which is based on Phoenix synthetic star spectra for supergiants, because atmospheres of FU Ori-type stars can be approximated by supergiant spectra. So we computed some synthetic spectra, like here the synthetic spectrum is compared with observed spectrum of FU Orionis. The match is not very good, but the model is still in developing, so should be better in the future. And yes, the model here on the left plot we see temperature distribution for FU Orionis, this, and with the smooth case without any disk inhomogeneities. Here we see that I can introduce in the model some disk inhomogeneity by a priori change, of the temperature, by introducing some departures from the expected temperature distribution. And the model produces such pictures. Depending on band, I can turn the rotation on. Here is the disk inhomogeneity caused by the temperature differences. And once we turn the rotation on, we can produce light curves, synthetic light curves, which have similar amplitude like those variations visible here. And also the color change, which the synthetic light curves reproduce also color changes, observed color changes. Maybe the scatter is big, the observing scatter is big, but the tendency is correct, and we have also many some observations in other filters which confirm the slopes, the difference between the slopes. And yes, okay, okay, we can also, using the model, determine where on the disk the disk inhomogeneity is most probably located. Of course, the position of the disk inhomogeneity changes depending on the light curve morphology, because the light curve, of course, changes with the time scale of few months. But the picture shown here we see the regions from 0 to 0.33 AU, astronomical unit, and the disk inhomogeneity indicated by the model is located at 0.08 AU. And the three-dimensional global magnetohydrodynamical simulations made by Sawan Su in 2019 showed that FU Orioni disk should has some due to different effects in the disk related to the enhanced accretion, has also some filamentary structure at the same region which was indicated by modeling of MOS data and multicolor data obtained from the ground. And I propose to concentrate on this picture because it shows for actually this atmosphere optical depth 1 in convention of his paper. Yes. I didn't discuss the further segment 2 variability. I remember you. I will show you segment 2 is here, but in zoomed version is visible here, which is also different than the segment 1 or segment 3 variations. It shows probably the final stages of mass accretion. We see that here is the most light curve, the dark, the red points, and observations from South Africa and from Mount Sukhora overplotted. And variations in U filter are much higher, and here we see color magnitude diagram U minus V and V are much higher than observations obtained in any other bands in B, VRI. Ultraviolet variations are much higher than in other bands, which is probably the evidence of some, let's say, hot phenomena, but some non-uniformity in the boundary layer, which is surrounding the star. Actually, the existence of boundary layer was in the last year confirmed by ultraviolet HST spectra by a student of Lindland. I was also analyzing in the past these 646 puppies, which is in general showing the same behavior as FU Orionis. Here I also calculated broadening functions using archive KEK spectra from KEK archive. The broadening function probably show some movements of disk inhomogeneities in the time scale of 1 day. You see here data obtained night after night and in the time scale of 1 week. And yes, this is some general conclusions about longer and shorter term oscillation visible in Orionia, also these 646 puppies. Actually, I'm organizing campaign to make observations of FU Orionis from 9th November to January 5 next year, because it turned out that TESS mission is still extended, and in this year TESS will observe Orion for two months, for almost 58 days. I submitted several proposals for time series high resolution optical and infrared spectroscopy. I will tell you why infrared is important as well, and some ground-based observations. The goal is to make maybe a movie of the inner disk and confirm or change my previous findings presented during this talk, maybe to identify the mechanism leading to FU Ori-type outbursts. Yes, infrared observations are important because the infrared is sensitive on this region. Visual observations are sensitive on phenomena occurring closer to the star or at the disk homogeneity. Okay, so if you have time, you can support the run. It would be very welcome. Thank you very much.
Yeah. Thank you, Michał. Any questions or comments?
Yes.
Thank you for your talk. FU Orionis is the first type object for.
We don't know, maybe class 2, but actually I should maybe highlight this more detail during this talk. Class 1 and class 2 stars objects don't differ very much. It depends on the, how much of the outer envelope is obscuring the disk, and maybe sometimes the star geometry also plays the role. Because class 1 objects are more embedded than class 2, and of course younger. FU Orionis is probably class 2 object.
But probably this luminosity is dominated by disk.
By disk, yes. I didn't mention, yes.
When let's say star starts to dominate.
Star can dominate the phenomena visible, for example, here probably is not out. This is probably not the star itself, probably the envelope which is surrounding the star, because the magnetosphere during FU Orioni-type stage, during FU Orioni stage is crushed. The disk is very close to the star, and it's completely encircles the star. It is something like merges with the star, or something like that, for a while. And maybe some effects visible here are from the hotspots on the star. And this is why the variations in U band are much higher than in V, for example.
Okay, because I wonder, let's say, we have some picture of star formation, we have Hayashi line, but in fact, let's say, here there is no star on Hayashi line visible, but disk.
Disk.
Let's say.
So
from which moment it is, let's say?
I think in class 1 objects we can say that there is a star inside. Of course, there are no thermonuclear thermonuclear fusion is probably still not operating. Maybe in the end of class 2. I don't exactly remember actually when.
Okay, so say this stops dominate at the end of let's say
after class 2.
Class 2 object.
Yes, I will show maybe the first slide. Yes, this is something like where it is. Oh yes, this is best visible here. Class 2, still accretion from the disk. Yes, planets are still formed inside, but after this depletion, there is some remnant debris disk around the star. On the star, stellar light is, the stellar light is dominating everything what we see in visual bands, at least. Yes, this is the scale.
Thank you. See, Łukasz, have a question?
Yes.
Yes, hi, Michał, that's great. And thanks for using BHTOM. I was just wondering from the BHTOM perspective, so what would be your most optimal and ideal scenario for the follow-up in terms of, the cadence? I know we can't beat most or tests from the ground, so, but anyway, would you be rather interested in very long-term multi-band campaigns like once a day or once a week? And then also what would be your optimal accuracy of the measurements?
You mean about FU Orioni campaign or in general?
Well, in general for YSOs, yeah.
In general, I think observations obtained once per week, even once per month would be sufficient to characterize most of our candidates. In case of FU Orioni, it is different case because we are searching for small light changes. The cadence could be as much as often as you can, a few times per night even.
Okay. Yeah. So, great. Thank you.
Any more questions or comments? If not, let's thank Michał. Thank you very much.
Sure.
Thank you. And the next seminar in 2 weeks, happy Easter. And in 2 weeks, we're going to see talk given by Mark Słowacji about the binary stars and all those.
Hello.
And please fill your name.